Hi, my name is Eleanor Williamson, and I am a I'm a postdoctoral researcher at Auburn University. I also got my PhD at Auburn University extremely recently, which is very exciting. So now I am lucky enough to be Dr. Eleanor Williamson, and I am quite grateful to this program for selecting me as a future leader. So thank you so much for that. It's a really wonderful opportunity. Um, I am here talking today about my research, and my title is Quantifying Color Using a Spectrometer to Diagnose Gas Density Within a Plasma. And my goal is that by the end of the talk, I guess, is a fairly obvious goal, but by the end of the talk, you should be able to understand the title, at the very least. Here's an overview slide, and I'm constructing my overview in terms of questions. And the goal of this talk and the goal of these questions is that anybody watching this talk will be able to answer all of these questions by the end. So the first question, of course, is what is a plasma? Followed by why is my diagnostic important? Why do we care? How does my diagnostic even work? Does my diagnostic work? It's not a very good diagnostic if it doesn't work. And how can it be used? Does it turn out to be useful? So without further ado, let's get right into discussing what is a plasma. Plasmas are the fourth state of matter. They are actually the most common state of matter in the universe. We are typically most familiar with the first three states of matter, that is solid, liquid, and gas, and we're very familiar with these in terms of water. So we're familiar with ice. That's the solid form of water. We're familiar with water, just the liquid form of water that we drink. And we're familiar with water vapor. You take a saucepan, you heat full of water, you heat it up, water evaporates, now you have gas. Well, what happens if you take some of that gas and you put it in an enclosed chamber and you heat up that enclosed chamber, you have lots of little atoms, lots of little neutral atoms, and suddenly electrons start popping off as you add energy. And what you end up with the plasma is a bunch of ions, that is the neutral gas particles where, the gas particles where the electrons have popped off, and the electrons, the negatively charged electrons, sort of all in this soup of positive and negative. However, um, phase transitions tend to happen gradually, and so what is more common is a combination of gas and plasma. So the material that I work with is actually um, quite a bit of gas and quite a bit of plasma, where you have a soup of neutrals, positively charged particles, ions, and negatively charged particles, electrons, all working together. So that's basically what a plasma is and what it is that I'm working with. Where have you seen a plasma? Well, plasmas occur throughout nature and in a variety of applications. The applications that most people are familiar with, plasma televisions, of course, are the most common. Stars, our sun is a plasma, lightning is a plasma, and my favorites are nebula and the northern lights because they are so beautiful. Other common forms of plasma are plasma cutting, semiconductor manufacturing, and fusion research. I come from a lab group that does quite a bit of fusion research, and so to some degree, that's my favorite application on the subject. So that's a plasma. Neutrals, as I mentioned before, are present in the low temperature plasmas that I work with. The low temperature plasmas that I work with are still quite hot. Matter enters the plasma phase gradually, as I mentioned before. What's particularly interesting is that the presence of neutrals does play an important role in plasma physics. As it turns out, plasma physics, because the plasma is positively and negatively charged, has its own set of interesting dynamics that's controlled by electricity and magnetism and fluid dynamics. But when you put neutrals in there, some things change a little bit. And if we're going to study what changes a little bit, we need to be able to measure the neutrals. However, this can be difficult for a variety of reasons. And so the purpose of my diagnostic is to measure that neutral density. I will note at this point that I'm using neutrals, gas, Interchangeably, they mean the same thing. The neutral density is the more technical way of putting it, but it's the same as the gas density. So how does this work? All right, let's start off with a nice energy level diagram. This is the energy level diagram of an argon atom. So an electron starts in an upper level state, an excited state, and descends to a less excited state. And when it makes that transition, it emits a photon. And it emits a photon at a particular wavelength. I then use a piece of equipment called a spectrometer to take all of the photons that are emitted by the plasma and essentially sort them by wavelength. What's incredibly cool about the spectrometer and our ability to use the spectrometer is that every single one of these wavelengths corresponds to a different energy level transition. And so if we look at a particular wavelength, we know exactly what the upper and lower energy levels are for that transition. The other really cool thing about the spectrometer, the particular spectrometer that I use, is that we actually get a photon count from it. We're not just getting an arbitrary unit of intensity. The way I calibrate the spectrometer, we can figure out exactly how many photons are coming off at a particular wavelength, and that's pretty magical. So we take a photon count, and as I mentioned before, I guess I didn't mention it before, we take a photon count, and that enables us to do a measurement of the excited state density, of the upper level density. So we have the transition from the upper level to the lower level, and the photon counting allows us to figure out what the population is of the upper level. So the way this works, here is a particular line from that previous graph, and we fit a curve to it. This is simply a way of figuring out what the photon count is. We call it radiance. It's just photon count in a different unit. And here's the equation. I'll talk you through it, and then I'll discuss in broader terms what's actually going on here. The 4 pi to radians is simply a geometric unit. The radiance is the photon count. This A value is the probability of an electron transition. The h nu is essentially the transition energy. It is the transition energy, and it's related to the wavelength. And L is the length of the visible cylinder of plasma. So what's really going on here is that if you have a bunch of electrons in an upper level state, and there's some probability of them falling, and you know exactly how many are falling because you can count the photons, you know exactly what the population is of the upper level in that atom. And so we use this equation to do just what I just said, and we get a population of the upper level. So now what? We have a population of the upper level. Now we need to get a ground state population. So we use an atomic model. The atomic model that I use is called Colruyt Pi, and it was written by, it's a piece of code that was written by a former grad student in my former lab group. And essentially, you plug in experimental conditions, electron temperature, electron density, some geometric factors for the chamber size, and out pops the population, that is the density of the excited state divided by the ground state. Again, the density and the population essentially mean the same thing here. Now, the population of the excited state and the population ratio can be combined to get the density of the ground state. And of course, that's exactly what we're trying to do. That is the entire diagnostic. And so with that, we are able to get a functional diagnostic. Well, what happens if we use it? Here is a chart from one particular spectrum. Remember that every single wavelength produces a neutral density, a gas density from one particular upper level. So we can get quite a bit of, we can get one neutral density for every single wavelength in that spectrum. And so here is a series of wavelengths, and we get a 5% standard deviation across the collection, which for plasma physics is an incredibly low number. All right, so we have a diagnostic, now what? Let's use it. The primary experiment on which I use the diagnostic is the compact toroidal hybrid, that is CTH at Auburn University. It is typically used to make high temperature plasmas used for fusion research, but in my case, I use it to make low temperature plasmas so I can get partially ionized plasmas. The vacuum chamber, so here's a picture of the experiment, and here's a schematic of the plasma. Oops. The vacuum chamber itself is about 1.5 meters in diameter. The plasma is created using microwaves, that is waves with a frequency of 17.65 gigahertz. The plasmas I use are consistently argon because of their prevalence in low temperature plasma physics. And the other thing that's worth noting about the plasmas that I make is they are very short-lived. The plasmas that I make last 100 milliseconds, which is a very, very short plasma. That's about 0.1 seconds. So all of the science we do has to be done quickly. Here's just the schematic of the plasma itself, and in addition to this being pretty, which is always a good reason to show something, the most interesting thing about this is the magnetic fields. So the color of the colors within this graphic represent the strength of the magnetic field. And so as you can see, there's not a lot of consistency. There's consistency as you go around, but there's a lot of twisting. So that's an interesting fact about the experiment in question. All right, does it work? The answer is yeah. The results that we have suggest that the gas density diagnostic does work on CTH. That doesn't mean we can say it works everywhere, but it does work on CTH. So this is an experiment I ran in which I made a number of plasmas, and for each plasma, I kept the amount of gas that I was putting into the chamber exactly the same. What I was changing for each plasma was the amount of power that I put into the chamber. Every electron that is in that chamber comes from a neutral atom, and so in orange, you see the neutral density. In blue, you see the electron density. And what you would expect to see is that as the power increases, the neutral density drops, which is exactly what you see, and the electron density rises by about the same amount, which is exactly what you see. So that you don't have to rely on your eyes, I also show the combined electron plus neutral density, and that should be staying roughly constant, and in fact, it stays roughly constant. And this set of results is a fairly good indication that this particular diagnostic works. Okay, well, it works, but is it useful? So what we do on CTH is donut shaped. And what I'm able to do is create a current, cause the electrons to flow around the plasma chamber, creating a current. So you can see the electrons in red. And as the electrons flow around the chamber, they get slowed down by neutrals. Those are shown in blue. And those provide a drag force. And the the resulting current can be both predicted and measured using a pretty basic equation. Voltage is current times resistance. And then as you have more neutrals, the voltage will drop, and as you have fewer neutrals, the voltage will rise. This is a set of results we took with exactly that previous concept. In blue, we have the measured loop voltage. So that's the actual voltage that is measured in the experiment. In purple, there's a calculated loop voltage based on modeled parameters. I wouldn't worry too much about that. But in red, there is a calculated loop voltage based on theoretical parameters and, importantly, neutral density. And so the neutral density is in this data. And what you see is fairly good agreement between the blue, which is the real value, and the purple and the red, which is the predicted value from two different sources. And this is important for two reasons. One, it suggests once again that the neutral density is working. And two, it suggests that the neutral density is actually useful. And that's a really, really exciting result. So in conclusion, I've shown that the spectrometer can be used to estimate photon count. The photon count from the spectrometer can be combined with the ratio of excited state to ground state to estimate gas density. The results show that the diagnostic works, and the results show that the diagnostic is useful. Thank you.